Okay, so it is my great pleasure to welcome my friend and colleague Johannes Pollanen here, all the way from Michigan State University, to hang out with us and tell us about what he's been up to lately. So Johannes did his graduate work with Bill Halperin. Yeah, we're going back a ways. With Bill Halperin, excuse me, at Northwestern University, working on the physics of helium-3, liquid helium-3 at temperatures below a millikelvin or something crazy like that. Following on that, he went to the lab of Professor Jim Eisenstein at Caltech as a postdoc, where I met him. I'd arrived a couple of years before, and then we hung out for a couple of years while he was attempting to build a fridge that could go even colder than Bill's made. Same kind of temperatures. Okay. So in his postdoc work, he pursued physics of gallium arsenide two-dimensional electron systems with surface acoustic waves. He then moved to Michigan State University in 2015 as assistant professor, where he remains today. He's had quite a good run there, with some of which we're going to hear about today. And he's also started a quantum computing company, AeroQ, which is pursuing quantum computing using electrons on helium. Perhaps we'll hear a little bit about that. So anyway, it's great to see you and hang out. I'll let you take over.
Thanks a lot, Eric. And thank you all for coming to my talk here. Can the folks in Zoom hear me? Just to make sure. I'll take that as
yes.
Thank you. That disembodied voice from above is really awesome. But yeah, so I'm Johannes Pollanen from Michigan State University, and I'm going to tell you about work that we've been doing in my group over the last several years. It's a laboratory for hybrid quantum systems, where we are taking distinct but interacting quantum systems, taking two or more of these. They can be various kinds of objects, single electrons, circuits, and interfacing them with one another, both from the perspective that we want to understand the ever more complex fundamental physics of engineered synthetic and hybrid quantum systems. But also we want to try to utilize that kind of understanding to maybe do something for quantum information science, make some kind of quantum computing kind of technology. And the story that I'm going to tell you about mainly involves this funny trapped electron system that we can form on the surface of superfluid helium, and also quantum circuits in the form of qubits. So yeah, but let me just give a little bit. I mentioned why we sort of like these hybrid and synthetic quantum systems, and really there are two reasons. One of them is a fundamental one. Nature fundamentally speaks a quantum mechanical language, and these kinds of systems allow us to interface these distinct quantum objects that have often multiple interacting quantum degrees of freedom, and that's a lot of fun from a fundamental perspective. And it even opens a door where we can study these phenomena at the level of single or handfuls of quanta, so excitations of microwave photons, qubit states, piezo-phonons, these kinds of things. The other aspect involves, the possibility of someday making future quantum technologies, say for, quantum simulation or sensing, communication, signal transductions, or computation. And so it's really this kind of, coupling between fundamental physics and the development of quantum technologies that drives the interest of the folks that work in my group and myself also. Now, before I get to the specific highlights of the things that I'm going to tell you that we've been doing recently, I kind of want to just give you kind of a 10,000 foot overview of the different kinds of things that are going on in my group, because I'm not going to be able to tell you about all of them in my talk. And more or less everything that we do in the laboratory for hybrid quantum systems can be grouped into one of four broad categories. So we are working with this quite unique trapped electron system and developing hybrid systems with that. So here, what you should have in mind is this system of electrons that floats above the surface of superfluid helium. These electrons float in vacuum about 10 nanometers above the surface. And what we're trying to do is interface them with quantum circuits or devices that we fabricate on the substrate beneath the helium surface. And I'll say some more about our specific results and the kinds of directions that we're heading with this. We also have an active program working on superconducting circuit-based qubits, so like transmon qubits and the like. Actually, this is a wonderful realization of a collaboration that started here with your colleague and mine, Cater Murch. Cater really taught us everything that we know about superconducting qubits and made us into a superconducting qubit. It's really been very, very productive. And I'll say a lot about the kinds of things that we're doing there. Something I won't have time to tell you about is our 2D system work. So we have a quite active program in studying the emergent many-body quantum phases of matter that can form in two-dimensional electron systems like graphene or semiconductor heterostructures when you subject those systems to very low temperatures and high magnetic fields. And yeah, if you want to talk about that, I'm happy to chat afterwards, but I just won't have time to cover it. And then very recently, we've started working on hybrid systems based on NV center defects in diamond. And yeah, that's a lot of fun. But again, something I'm not going to have a lot of time to I've talked with some of you about it today, but I can say more if you want to chat afterwards. If at any point in time you get bored or you want to check out any of the other things that we're doing, you can check out our website, hybridquantumlab.com, or as my students make me do this, if you do Twitter or Instagram, you can follow us there as well. Okay, so I wanted to give, like I said, I want to give you just kind of a highlight reel of some of the things that we've been doing in my group over the last several years. This is by no means exhaustive, but it kind of covers 3 vignettes that are connected, as you'll see, to one another. 3 stories of synthetic and hybrid quantum systems where we've learned some interesting things with these kinds of systems. The first part will be work that actually got us into the superconducting qubit game with Cater, where we coupled superconducting qubits to quantum fluids. And it turns out that if you take superfluids and interface them with superconducting qubits, you can learn some interesting things about the circuit quantum electrodynamic vacuum via the superfluid, or you can even use the quantum fluid as a tool for investigating the coherence of these qubits. And I'll show you some results on that. In the second vignette, what I will tell you about is our work demonstrating the first coupling of this electron on helium system to evanescent piezoelectric surface acoustic waves and the kinds of devices for charge pumping that we can make with those systems. And in the final part, I'll tell you about very new work that we've been doing, developing an analog of circuit quantum electrodynamics using piezo-phonons, which is essentially now called circuit quantum acousto-dynamics, where we couple the superconducting qubit degrees of freedom to propagating surface acoustic waves on piezoelectric crystals, and why those kinds of hybrid systems are fun. But again, with each of these, you'll hear this repeating of, oh, this is fun because it's great for fundamental science, but also there might be some fun technological applications, and that's true for all of these different stories. And the good news is if it turns out you don't like any one of them, you don't have to wait very long. The story will change and you can hear about the next one. Okay, so I'll just give since this talk is going to have a lot of stuff about superconducting qubits, I just want to give you a quick overview of superconducting qubits, if that's not the thing you think about all the time. It certainly wasn't until very recently in my life. So what we want to do is we want to make an engineered circuit into a qubit. And so what do? We need a 2-level system and out of a circuit. And we better use a dissipationless material because qubits are very fragile and quantum states are easily decohered. So let's use a superconductor. And the simplest circuit that we can make is an LC oscillator, right? We can inductor, capacitor, the energy is stored, is shared between the 2 of them and oscillates back and forth at the frequency of the circuit. And if you take this thing and you cool it down to very low temperatures and you engineer the frequency so that it's sufficiently high, you can quantize this circuit. It will become a quantum mechanical object. It will be a quantum harmonic oscillator where the conjugate variables are the phase and the charge degrees of freedom in this circuit. Well, that's great. One big problem, however, is that it's harmonic oscillator, so these energy levels are equally spaced, each of them by h bar omega, and so you can't isolate any one of them. If I apply a microwave signal to try to take me, say, from the ground state to the first excited state, and I apply, each one of those, if I keep applying that signal, it'll just jump around in this ladder of harmonic oscillator states, and I can't isolate any 2 states individually. So that's not so great. So we like to say that Schrodinger's cat does not like harmonic oscillators as qubits. It turns out there's a very simple way to get around all of this, and that's by introducing a nonlinear inductive element. It's called a Joseph's injunction. It's just 2 superconductors sandwiching an insulating region. This is what one of those devices actually looks like. One of those junctions looks like. It's represented by this X. And what this thing functions as is a nonlinear inductor that with the inductance depending on the current that flows through this device. So all we've really done is taken that inductor and replaced it with a Josephson junction. And we can again quantize the Hamiltonian that describes this circuit. And if we cool it down and it has sufficiently high frequency, this thing will be in its quantum mechanical ground state. But instead of a parabolic harmonic potential, we get this cosine potential for the qubit energy levels. And they correspond again to just charges oscillating and currents flowing through the tunneling across the junction. But the nice thing is since this is anharmonic, these energy levels are just a little bit different from one another. And so we can isolate two of the energy levels by just applying a sufficiently narrow microwave signal in frequency to manipulate this thing as a qubit. I should mention I'm happy to take questions at any point in time. So if you want to say things, feel free. So the superconducting qubits that we use in my group we use this three-dimensional architecture where the qubit lives on this little chip on the center, and we house it in a three-dimensional microwave cavity. It's literally something that's made in the machine shop. We just mill a slot into this 3D cavity, and then we can talk to the qubit, which is on this chip, via the electromagnetic modes of this cavity by sending in signals through here. So if you zoom in on that chip, what you find is one of these little Josephson junction elements right here, and this essentially forms the heart of the qubit. And these wires that extend up and down out of the pane of this image connect to large millimeter scale antenna pads. And those antenna pads form essentially just a dipole that we can then couple to the electromagnetic degrees of freedom of this microwave cavity. Oh, and I should mention, we typically engineer these things so that they have so that both the microwave cavity and the qubit have frequencies in the 5 to 10 gigahertz range. And so that's really great because 5 gigahertz in temperature units corresponds to about 250 millikelvin. So if we take this thing and we put it on the mixing chamber of our dilution refrigerator, this thing, both the electromagnetic modes in the box and the qubit initialize passively into their quantum mechanical ground state. They just cool down and then they're in their ground state and we can start playing around with the quantum system and do all kinds of things. But let me say a little bit more about how we actually measure these kinds of qubits. It's actually pretty simple. What we do is we borrow a page from quantum optics. So you can think about this qubit in this microwave cavity very much like an artificial or synthetic atom living in an optical field. So if you take, that's cavity QED. If I take an atom, put it in an optical cavity, that system will be governed by the Jaynes-Cummings Hamiltonian. Similarly, this system will be, with this synthetic atom in this microwave cavity, will be governed by the Jaynes-Cummings Hamiltonian. And so we're just doing essentially quantum optics with a fake atom in a microwave box. And this Hamiltonian it's really very simple. It has a qubit term. It has a harmonic oscillator degree of freedom. That's the electromagnetic mode of the box. And then it has some coupling between the two of them, where the coupling is determined by this constant G. Now, we operate in a regime where the qubit and the cavity are dispersively coupled to one another, which means essentially that the qubit is relatively far detuned from the cavity and is very weakly coupled to the electromagnetic field. This G, in other words, this G squared over delta parameter is small, and we can do perturbation theory on this Hamiltonian. And in particular, I want to draw your attention to something here. So I mentioned that we send microwave signals into and out of this box to control the qubit and read it out. All we're doing is measuring the microwave cavity itself. And you can see that when we operate in this dispersive regime, the microwave cavity, which is this harmonic oscillator degree of freedom, picks up a frequency shift that depends on the state of the qubit. So whether the qubit's in the ground state or the first excited state, the cavity resonance actually shifts around. And that's how we do the readout and control. It's just perturbation theory. Okay, so that was your primer on superconducting qubits. We'll come back to some of the details in future slides, but what we did, now I'm going to tell you about the first kind of interesting new thing that we did with these kinds of systems, is we coupled them to a superfluid. So you might say, why on earth would I ever want to couple a superconducting qubit to a quantum fluid? And we had some particular reasons that we thought this would be fun. In particular, since the superfluid is dielectric, we wondered, hey, could we introduce a frequency tunable circuit QED vacuum that we can just tune around and see what happens. Fundamental physics. We thought, hey, actually these kinds of helium immersion cells where people put quantum devices into helium baths are actually a technique by which in other communities, it's known that you can thermalize the electronic degrees of freedom of the device better. And so we thought maybe that is a good idea in this context. Nobody had tried it. And perhaps this has the ability to improve the qubit coherence. And then some of you know, I think that probably everybody knows this. So Kader is not just a fantastic collaborator, he's also a wonderful artist. And whenever he writes a paper, he makes some little sketch. He's always sketching something. I don't know how he has time for all these things, but he made this really wonderful picture that went along with the paper that we wrote about these results. And so we went ahead and built, with these kinds of motivations in mind, we built a hermetically sealed superfluid leak type 3D microwave cavity and set ourselves to filling this thing with superfluid and seeing what happened. Okay, so we learned a bunch of things in doing this. So I'm going to show you some measurements. Every measurement that I'm going to show you has it's two comparisons. One without helium and one where we've filled the 3D cavity completely with helium. And then we compare the results. And so we can see all kinds of things. So first off, the cavity frequency shift, because helium's dielectric. It just moves the harmonics, you're essentially taking a capacitor and changing its dielectric constant in many ways. And that causes frequency shifts of the cavity. The qubit also has capacitive elements. And so the qubit transition frequency is also great. So it turns out that's one thing, but you can actually be more quantitative and you can analyze these shifts, the spectroscopic properties with and without helium in the context of a generalized Jaynes-Cummings Hamiltonian, and you can extract all kinds of parameters of interest. So for example, the Josephson energy of the qubit doesn't seem to care about whether you put helium in there. That's not terribly surprising. It's not a capacitive element. The charging energy, however, changes by exactly what you would expect from the modeling of filling the cavity with superfluid. But actually there's a lot of numbers here. If you're interested, we can talk about it, but there's kind of two takeaways that we learned from this. So the dielectric superfluid does two things. It modifies all of the capacitive energies of the problem, of the cavity, of the qubit, just because it's slightly dielectric, just a little 5.5% different from vacuum. But it turns out it also modifies the 0-point fluctuations of the microwave resonator. So we can see that in particular in the coupling between the cavity and the qubit. In order to fully understand the changes that you see in this coupling when you introduce a superfluid, you have to take into account the fact that you change the 0-point energy of the vacuum.
So is it coming through the capacitance change?
It is essentially still just a capacitive effect. It is, but it's buried. It's kind of instead of being a direct capacitor, it is ultimately a capacitive effect. They're all capacitive effects, but it renormalizes the 0-point.
Can you quickly remind me the Baire and Dress difference?
Yeah. Oh, right. So this is related to that dispersive perturbation theory Hamiltonian thing that I told you about. So the Baire cavity frequency is the cavity frequency if the qubit were not in the cavity. The Dress cavity frequency is the frequency at which the cavity shifts because of the qubit in its ground state in the cavity. So the two, at low temperatures, you really can't think of these things as independent objects, right? The cavity and the qubit hybridize largely with one another and strongly influence each other's behavior. Okay, so that's kind of fun. So we can understand quantitatively what the superfluid's doing. Terrific. What about the coherence? So this is where this is this question about thermalization, and it actually turns out that when you introduce the superfluid helium into the environment, the coherence time of the qubit actually gets better. So the qubit becomes more coherent when you put the helium in, and that you can see in this plot right here, where we did a bunch of measurements of T2 and the pure dephasing rate. And the thing I want to draw your attention to is the green open and closed square triangles are the pure dephasing rate of the qubit, and at low temperatures, pure dephasing time, sorry, it becomes more coherent by about 20% at low temperatures when we introduce the helium.
Good question.
Yeah.
How did you extract T5? Is it just echo minus Ramsey?
Yeah, so we just measure T1 and T2, and then
2T1 minus T.
Exactly.
Okay, cool.
Yep. And so that's cool. Now you might say, why does that happen? And so it turns out for the kind of qubit that we use in this experiment, it's a single junction transmon. And it's known largely that the dephasing of that qubit is dominated by residual cavity photons from some hot port part of the microwave circuit. So the microwaves, you have the cavity sitting there, you try to attenuate all the microwave photons out, but there's always some residual population of photons that are living there that leak in from some hotter part of the environment. And in fact, that dephasing rate has been known in the superconducting qubit community for some time. And if we take this model as being the dominant effect of the dephasing in our qubit, we said, how much would we have to cool down the microwave environment by adding the helium to explain this difference? And it turns out you only need about 10 millikelvin of cooling of the residual photon population in order to see that improvement in cooling. So
what is the effect of reducing the thermal fluctuation? Because you're in a superfluid state.
yeah, so here it's the thermal, we think what we're doing is we're actually just cooling, we have other experiments where we don't believe we're cooling the qubit directly, but what we're cooling is some part of the microwave environment that is not super well thermalized without the superfluid. So there's just microwave radiation from something that's about 80 millikelvin coming into the cell. Does that answer your question?
Yeah. No, I was thinking that since you are using a superfluid, it's probably any kind of thermal fluctuation in the system is probably reduced by the superfluids.
Exactly right. You probably is thermalizing many things. It's probably reducing the thermal fluctuation of many things that then indirectly increase the residual photon population in the cavity. The other thing, so I'll mention one interesting thing, that this idea of this kind of photon induced dephasing was very much in vogue when folks started working on superconducting qubits in the 2007 kind of time. But actually it was known in a completely different context much earlier by my theory colleague at MSU, Mark Dickman, back in the 1980s. He predicted the same kind of thing, but in a slightly different context. Anyway, so this was just the highlights of the paper. There's a whole bunch of detail in this paper that we wrote that has more gory detail, and I'm happy to tell you about it, but I want to jump to the next. Shoot, great.
So just out of curiosity, what caused the T2 or T1 to be saturated
At low
from
temperatures.
0 to 50 millikelvin?
Yeah, no, that's great. That's a great question. So it turns out helium-4 is, and many things are notoriously difficult to cool down to, 10 millikelvin. So many of the things like the superconducting microwave cavity, the silicon chip, all this stuff doesn't want to really thermalize terribly well. It turns out helium-4 also doesn't want to thermalize terribly well. There's a very large thermal Kapitsa boundary resistance between cold metals and liquid helium. And it's actually pretty hard to cool helium-4 down into the tens of millikelvin range. So we think the helium is actually thermally decoupling down there.
So you think it's still like, it's just the thing is not thermalizing.
Exactly.
So if in principle you thermalize things,
Yep.
it's like you will
It'll
give
be
it
a lot
better.
better.
It's not something else that limits the
No,
T2 or
no,
T1.
no. In our devices, I think that there's no evidence that in our particular, I think in certain situations, the devil's in the details a little bit there. In certain situations, I think it could be other things. I think in our case, if we had a better thermalizing agent, say helium-3, which we've been wondering if we should maybe do this experiment with, then it could cool even further.
I see. Interesting.
Yeah.
What is the scaling of this with temperature? It should be just exponentially? The scaling of T with temperature in principle, is it exponentially suppressed? Right, because you're just literally, you're not populating the energy levels. It should be just,
right.
I see. Okay.
I haven't thought about this. I should think about this more before I answer definitively, but I think that's right.
Thanks.
Okay. So let me change tracks now. So if you didn't like that part, we're going to talk about electrons on helium and piezoacoustics. This is another hybrid system that is also very fun. And the theme that ties these two together is the helium. So we're quite unique in our in the world in that we are one of very few groups that study this unique electron system. So what I want you to have in mind is these electrons that float above the surface of superfluid helium. It's a very strange but very well characterized system. The reason these electrons live above the superfluid surface is the following. If you were to place an electron here, the helium is again dielectric, as we just described. It slightly polarizes under the electron and forms a little positive image charge. And then the electron is drawn to its own image. It sees that negative charge sees its own positive image and just wants to go to it. So it wants to go toward the helium, but it can't go in because the helium, the electronic orbitals of the helium-3 atom, the helium atoms themselves are completely closed. So there's a Pauli barrier for the electron to go. There's no open state that the electron can jump into. And so these two things balance, and it floats about 10 nanometers above the helium surface. So we just sprinkle them on there and then they float naturally on the surface. And this is a really fascinating low dimensional electron system.
In this state, they form what's called the Wigner crystal.
They do indeed. So I'll show you some data that we have of quasi 1D Wigner crystals that we have. But yes, so the system's extremely clean. It has, for a point of reference, it's the cleanest two-dimensional electron system in condensed matter. It's about an order of magnitude or more cleaner than the best MBE grown gallium arsenide 2DEGs that can be obtained. And that's really just because there's helium and there's electrons and there's nothing else. So it doesn't see the disorder down here because you can make this helium very thick and it's, yeah.
So just a general question with 2DEG. So say you have gallium arsenide, indium gallium arsenide, and you trap a layer of electron. Is there still crystal momentum, the crystal, is there still an idea of lattice there, or do you just have a mushed out electron that doesn't really have a spatially dependent density?
So the electron in gallium arsenide, the density is spatially dependent, but that system is quantum degenerate. So the electrons largely overlap with one another. And then the in-plane charge probability of all of those electrons interfere. Here it's very, very different. Here the electron density is extremely low. So these electrons are much more classical than the ones in gallium arsenide. So to give you you really should be thinking about these as like individual points that are separated by a large distance. So to give you a sense for these densities, this spacing is micron scale or tens of microns between electrons. So they're very, very far apart from each other.
And they form crystal mainly because the Coulombic interaction?
That's right. So yeah, so never mind. This is great. I'm glad you're asking. This is much better this way. So yeah, you can form, because of the Coulomb interaction, it's completely unscreened. You have these bare electrons above this mildly dielectric surface. These electrons repel each other intensely. And so the system can actually form one of two states, a strongly correlated electronic fluid-like state where the electrons have a high conductivity, or if you decrease the temperature and increase the density, they crystallize into a 2D Wigner solid, which has triangular symmetry. And like I said, this system is quantum non-degenerate, so the electrons do not overlap with each other in terms of their wave function, but it's not a classical system in the sense that the individual quantum degrees of freedom of these electrons are important. And actually, those are the ones that we want to manipulate ultimately for quantum information science. And because the system's so clean and there's only helium, the coherence times are predicted to be exceedingly long, both for the spin degrees of freedom and the charged motion. And because the system's so highly controllable, we can fabricate all kinds of devices underneath and really do very cool, fun physics with this system, as you'll see.
Johannes?
Yes.
You can do this with any noble gas?
So helium's the only one that will remain liquid. As some of you know, you could put solid neon down or solid krypton, solid argon. These all work great too, but they're not as clean as helium, certainly not from the perspective of these kinds of mobilities. You can't get these kinds of, these mobilities are only achievable on helium. So I mentioned that these have been, these are interesting from the perspective of qubit. So there's a bunch of potential qubit platforms that can be developed with these electrons on helium. There are charged qubit states that are motional. So the electron can bounce up and down in a quantized fashion normal to the helium surface. You can engineer traps that confine the electron motion laterally, and you can get in-plane quantized states, again, charged motion. Or if you apply a magnetic field, you can manipulate the spin. And there's a variety of groups around the world working on this. And this is in fact, ultimately the charge plus spin ones are associated with the ones that we think can make a large scale quantum computer based on this. The startup company that Eric mentioned earlier that I work with is pursuing. Now, but I'm going to tell you about hybrid systems here, like coupling these to weird kinds of devices. And in fact, there's a rich history of hybrid devices with electrons on helium. These are not pictures from my group, except this one. But you can, so with each one of these devices, what you do is you do some nanofabrication to make some kind of device that you can apply gate voltages to or high frequency signals to, and then you cover the whole thing in helium and then put electrons down. And people have used these to realize essentially classical Coulomb blockade point contact devices. My colleague Steve Lyon at Princeton has developed CCD arrays in CMOS where you can gate electrons up from one place to another with extremely high efficiency, much higher efficiency than you can achieve in, say, silicon devices where the electrons are in the CCD. You can make microchannel devices in which you can create quasi 1D confinement and then look at crystallization there. These kinds of microchannel devices are ones that we work with quite extensively in my group. But there's a lot of different kinds of things that you can imagine doing. It's really a fantastically controllable system in this regard. And so what we wanted to do was to couple these electrons to devices that allow us to launch surface acoustic waves. Now, what I mean by a surface acoustic wave is we take a piezoelectric crystal and we fabricate some interdigitated transducers on it. When we apply a high frequency signal to these transducers, it strains the underlying crystal and launches a surface wave along this crystal. And then if we put something like a two-dimensional electron system in the path of this wave, then there's an interaction via the evanescent coupling of the piezoelectric field of this elastic wave. And then via reciprocity, we can detect the surface acoustic wave that impinges upon this other interdigitated transducer. Now, what we wanted to do, because no one had ever tried to couple electrons on helium to these kinds of devices, is we wanted to just try to see if we could couple the electrons and move them with the surface acoustic wave. So pick up the electrons evanescently with the surface acoustic wave and carry them along in its direction and measure an acousto-electric response in these kinds of devices. And these kinds of surface acoustic wave, two-dimensional electron systems actually have a very rich history in semiconductors. So people have used them in gallium arsenide, in particular, to look at a variety of fundamental physics effects, like, they were used to detect the composite fermion metal at nu equals 1/2. They've been used to study electronic liquid crystals, the metal insulator transition, all kinds of exciting things. Actually, this is the context in which I learned how to do these things quite some time ago now, when I was a postdoc in Jim Eisenstein's group, where we looked at essentially bilayer quantum Hall systems with surface acoustic waves. And they're also interesting from the perspective of applied physics. So people have thought about, in the context of semiconductors, people have thought about using these as high frequency charge pumping devices for metrology. You can use them potentially to make spin entangling devices where you can have flying qubits that ride along on this surface acoustic wave from one place to another. This last one in semiconductors is tricky because if you take an electronic spin in a semiconductor and you start moving it around, it doesn't stay coherent because of spin orbit crystal fields and all kinds of terrible stuff in circuits. And so what we wanted to do was to see if we could make such a device with electrons on helium. And so what we did is we took a slab of our favorite piezoelectric, in this case it was lithium niobate, you can use anything essentially. And we fabricated some gates underneath this piezoelectric substrate that we could use to measure any charge imbalances that are created in the electron layer. Then we covered the whole thing in about 70 nanometers of helium and then sprinkled the electrons down on top. And then we tried to see if we could use the surface acoustic wave to push these electrons around. And this is just data of the acoustic response of this kind of SAW surface acoustic wave circuit. And if we look at the induced current on these underlying electrodes, we find that there's a resonance again, right where the surface acoustic wave is launched. And this corresponds to us essentially carrying charges from one of these electrodes onto the next. And we can see this resonant current that flows. And we can do a whole bunch of control experiments to make sure that we really are detecting the signal from the electrons on the top. The wonderful thing about this system is you can always take the electrons off and then see if the signal goes away. And you really know whether it's coming from the electrons or something else.
How
Or you can
critical
take
is how critical is the thickness of the
Yeah.
helium layer?
So it needs to be small to be able to, so here we're using the evanescent field of the surface acoustic wave that sticks out of the surface to grab a hold of the electrons. And that dies away essentially exponentially with it's about a wavelength out of the surface. If we made the helium much thicker than a micron or two, then the signal goes away. So we have to be within that evanescent decay field. Yeah, that's actually one of the controls that we can do. We can just make the helium thicker and thicker and watch the signal disappear because we're moving the electrons further and further away. And here's just some more of that data. One thing I want to highlight, this is, we looked at it turns out that you can do some simple modeling and you can convince yourself that the acousto-electric currents that you generate should be linear and the power that you apply, it turns out that's not terribly surprising. But those underlying gates that we use to detect the signal, we can actually use those to turn the acousto-electric signal on and off. And so we can essentially create an acousto-electric field effect transistor with this device by applying appropriate DC biases to the underlying electrodes. And so this really opens up the door for the first time for using these kinds of surface acoustic wave techniques to do precision control and experiments with this system. And that kind of proof of concept is great, but we want to do something into the future, and there's a variety of different directions that we're heading. So for example, one can imagine creating high frequency devices for measuring the conductivity of the electron system, for looking at, say, collective excitations of the Wigner solid. You could try to do this charge pumping thing that people did in semiconductors, but in this much cleaner system. Similarly, because the system's much cleaner, you might be able to imagine transporting a spin from one place to another using the surface acoustic wave. There are no spin orbit fields in the vacuum above the helium, but those are, I think, probably a little harder. One thing that we are working toward now is to develop dynamic and tunable acoustic lattices that we can interfere with the electron system. And this is what the concept idea of these devices looks like. We have these two interdigitated transducers. We're going to fire surface acoustic waves right at each other and create a 1D dynamic lattice, acoustic lattice here, and then have a microchannel of electrons that are commensurate or quasi-commensurate with that electron system. Now, we've actually, more than just this cartoon, we've actually started heading in this direction. So we can fabricate these kinds of microchannel devices that allow us to have really precise control of single or multiple electron chains, linear chains in the microchannel. This is what the actual devices look like. We have these reservoirs here and here where we store a whole bunch of electrons on the helium. And then we have this central microchannel in the middle that we can populate with, say, a single chain of 500 electrons or two chains of 500 electrons in that microchannel. And then we have back gates and side gates for tuning the confinement of that system. And this is data from transport data for one of these microchannel devices with the side and back gate voltages. So in this region here, we have no electrons in this middle microchannel. Then at some point, if we make the potential here a little bit more positive, we can populate the microchannel with an electronic fluid of electrons, and that's this high conductivity region here. This is the color map is the conductivity. If we keep increasing the confinement of the electron system, squeeze it tighter and tighter, whoops, that electronic fluid crystallizes into a quasi 1D Wigner solid in the microchannel. And I want to draw your attention to these little feather-like features on the side of this bird's wing. They correspond to discrete row formation of electrons in the microchannel. So down here, this bottom feather, that corresponds to a single row of 500 electrons. The next one is a second row, and a third one, fourth one. And we can just introduce them in a controllable fashion this way. So we haven't yet got, in these devices, we haven't yet got the surface acoustic wave part, but we got the microchannel part working. But it turns out that again, I'm going to make a plug for my theory collaborator, Mark Dickman here. Mark and his group have been studying this system of electrons subjected to a 1D potential with tunable strength as a playground for looking at commensurate incommensurate transitions. So where the electronic order that forms in the crystal of electrons has to compete with this underlying potential that you can tune. And they've been doing pretty large molecular dynamic simulations to try to look at like commensurability, matching features in the mobility of the electron system. And the neat thing that they've discovered in this theory is that if you make the strength, the interaction between this underlying lattice and the electron system is extremely strong, even in the case when the interaction strength is much, much smaller than the temperature. So even if this underlying lattice is only weakly coupled to the electron system, there's a strong change in the electronic order that forms in the electron layer. And that's really a correlation effect. If you pin one of the electrons, the Coulomb interaction in plane is going to really stick the rest of them.
So there is no disorder?
Yeah, there's no disorder. This is a correlation-driven matching. Yeah, this is the really wonderful thing about this, is you can really be in a regime where the disorder, you can try to introduce it in some systematic way, but you start from a very clean system for this. That's really the anyway, so they wrote up some nice papers on the theory of this, and we're going to try to realize it using surface acoustic waves. Okay, I have enough time to finish my talk. This is great. So I'm going to pause in case anyone has questions about the electron and helium part. Otherwise, we're going to jump back to superconducting qubits, but we're going to keep the saws. This is another fun hybrid system where we're going to, the theme is the same. We're going to put these distinct interacting quantum degrees of freedom together, get them talking to each other, have fun, and develop technologies.
So you showed these microchannels where you could sort of pin the electrons. You move them around just by applying electric fields?
Yep. So we can just slosh them around. We can pull the row out. We can deplete it. We can put it back in. Yeah.
And how do you control how much charge is actually on the helium? How many
You mean
electrons
overall, like how do we control
how
the
do you
overall?
introduce the electrons?
Oh yeah, this is a great question. So yeah, I said we sprinkle them. We really do that. We use a tungsten filament in the cell. So we just put current through a little light bulb filament that we have in the hermetically sealed cell. It heats up to several thousand degrees Kelvin. Electrons come boiling off. They hit the surface of the helium, and then they stay
It
there.
doesn't blast the superfluid helium out of the...
No, you have to be a little bit careful with this. If you got to go to like 1 degree Kelvin, so there's enough cold helium vapor in there to keep everything happy, but it just works. If you put the filament way too close to a thin film, it vaporizes. And I promise this last part I'll go quick because but there's a question. How do you ensure mechanical stability of the system? You mean to make sure, is the question, how do you ensure that the electrons don't just all repel each other away forever? Is that the question?
No, the question is, you're talking about a displacement of the order of nanometers or microns or something. How do
Yeah.
I make sure that you don't have any kind of surface irregularities or
So the
the
helium
place is not floating in mercury or something?
great. So yeah, the helium is a liquid. Everything else that is, any impurity will sink to the bottom of the helium. And then actually in these microchannel devices, it's very easy to control the helium thickness because the microchannel itself stabilizes the helium film via capillary action. So we draw up the helium into the microchannel via just, van der Waals essentially, and getting sucked in there via capillarity.
Thanks.
I think I broke I clicked and that was bad. Is this working again? Yes, I fixed it. Okay. So I get rid of this now. It'll just disappear. Okay, or it'll be fine. So yeah, okay, we want to couple now surface acoustic wave devices to superconducting qubits. And here's a picture. Here's a superconducting qubit. Here's some surface acoustic wave resonator, which I'll describe a little bit more. Why on earth would anyone want to do this? Well, it turns out this is really interesting for a variety of reasons. We can use the qubit to control mechanical degrees of freedom. We can explore exotic new regimes of circuit quantum optics, but using piezoelectric sound. And because the speed of sound is about 5 orders of magnitude slower than light, that means that the corresponding phonon degrees of freedom are 5 orders of magnitude shorter in wavelength than microwave photons at the same scale. And actually Amazon loves this fact. They have a large quantum acoustics team working to try to create essentially quantum computing with phonons. And that has other implications for, say, quantum communication or transduction of optical to microwave signals using surface acoustic waves. And we can engineer these surface acoustic wave structures to have frequencies that are also in the gigahertz range, so that when we cool this thing down, the SAW resonators will be in their quantum mechanical ground state as well, in addition to the qubit in the microwave cavity. Now, these resonators, which is what we're making, look like this. So we have, remember, the surface acoustic wave is this, like, essentially wave on an ocean, but on a piezoelectric crystal. And so what we do is we fabricate one of these interdigitated transducers in the middle, and that launches saws to the left and to the right. And then on either side, we fabricate little strips of metal. These are these blue lines here. And those work as acoustic Bragg mirrors that reflect the surface acoustic wave and trap it inside of this essentially nano-fabricated acoustic Fabry-Perot. And these devices are amazing because they're in your cell phone, and they're useful in a variety of classical telecommunication technologies. And so you can use essentially a classical coupling of modes theory to model devices and to engineer them to have the kinds of responses that you want, and then couple them to qubits and see if you can get those features to appear. And just to give you some sense, these are the kinds of the speeds of sound in lithium niobate, say, are about 4,000 meters per second. So we're operating with devices that have frequencies in several gigahertz range. And so here's what one of those devices actually looks like. There's a whole bunch of interdigitated fingers here, and then on either side there's an acoustic Fabry-Perot, and we attach it to these large-scale antenna pads. That it'll become obvious why we do that. And so we can use this coupling of modes theory, which you can just essentially look up in this, surface acoustic wave filters book, to engineer devices that have any kind of property you want. And so what we wanted in this kind of device was to engineer a single strong acoustic mode in the resonator, and this quasi-continuum of acoustic energy states that are on either side. So this is kind of like a dissipative quantum bath with a single piezoacoustic phonon mode trapped in the resonator. And then what we're going to do is we're going to take that kind of device we fabricated on a lithium niobate chip with these antenna pads, and then we flip a qubit directly on top of it. And so now the antenna pads of the superconducting qubit create a parallel plate capacitor with the antenna pads on the SAW device, and there's a direct capacitive coupling between the two. And then the name of the game is to try to understand Hamiltonians that look like this, where you have qubit degrees of freedom and now mechanical acoustic modes that look a lot like harmonic oscillator degrees of freedom, but in many ways they're very different, as you will see. So that's the name of the game. And then, so we actually fabricated these kinds of flip chip devices and put them in a three-dimensional microwave cavity, again, to cool this, and then we cool this thing down in a dilution refrigerator and do all the measurements.
How do you align these flip chip devices?
So these are really easy. We use these, the lithium niobate is polished on both sides, and we just use these big antenna pads. These are really big, and so the alignment isn't perfect, but they're big, and you just get them about right, and you'll get a lot of coupling.
Oh, okay.
Yeah, there are fancier ways. We don't have a what are those? Like a
backside alignment.
Yeah, die bonder flip chip thing that costs like $500,000. So we just do this on a microscope in the clean room by hand, or my students do. But I'll point out there's a number of interacting quantum degrees of freedom here. There's the SAW resonator, there's the qubit, there's a microwave cavity, and they all actually interact with each other. So just to show you, here's that engineered acoustic resonator response that we wanted. And here is the spectroscopy of the qubit. So the qubit that we have here, we can change its frequency by applying a flux to the squid loop that forms the qubit. And so as we tune the qubit through, we see that there's a nice avoided crossing with this single strong acoustic mode here. Plus, we actually impart all of these features onto the qubit spectrum. So in fact, we can reach many different regimes of circuit quantum optics in these devices. In particular, we can, through this avoided crossing, we find that the coupling to that single mode is on the order of 10 megahertz or more. So we're in the quantum acoustic strong coupling regime, but we actually access other regimes where we can cause the qubit to blink in and out of existence as it interacts with this quasi-continuum of acoustic energy on either side of that strongly coupled mode. So we can also go very far away in frequency from that acoustic, that strong acoustic mode. And out there, the device has this kind of response. This is again the simulation that we engineered, and we can measure the qubit loss and in terms of essentially T1, and we find that it tracks beautifully with the acoustic degree of freedom up here. And what this really shows is that we can use these kinds of surface acoustic wave devices as quantum acoustic bath engineering platforms, where we can create extremely sharp spectral features in the acoustic device and then interact the qubit with those. And so the next step is to try to generate some non-trivial superpositions of the qubit and have them have part of them decay into acoustic modes and be gone forever, and then get different superpositions that you couldn't engineer otherwise. Tater, if you're listening, there's no way he's on Zoom. He's mountain biking or something. But I think this would be in something that he would find near and dear to his heart. And then finally, there's one other cool thing that we demonstrated recently, which is that if you park the qubit way over here, very far away from this acoustic resonance, and you send a microwave signal into the cavity at the avoided crossing, then you should, in principle, if there's any coupling via free space to the SAW device, be able to populate the resonator with piezo-phonons. You should be able to take microwave energy and put it into phonons. And in that dispersive Hamiltonian that I showed you, you could regroup terms in a different way. And you can actually find that if you have a qubit coupled dispersively to a harmonic oscillator degree of freedom, the qubit frequency will pick up shifts. One of them is the Lamb shift. It's just associated with the coupling to vacuum fluctuations of the harmonic oscillator degree of freedom. But there's also a Stark shift. So if we change the number of phonons in the resonator, we should be able to shift the qubit frequency. And in fact, that's what we find. So if we drive this resonance, we can shift the qubit frequency down. And if we model this shift here corresponds to approximately a maximum number of 4 phonons on average in the piezo resonator. And so it turns out we can do a lot of, we can really turn the crank on the theory, but I'm not going to show you any of that. And it more or less matches what you would expect from perturbation theory until you go to very high power, where we think we're populating all kinds of other acoustic modes in this device. And I'll mention this device also hosts not just surface acoustic wave modes, but it actually has bulk phonon modes that we know we can couple the qubit to also. And I'm happy to say more about that later. But in the interest of time, that's essentially the story that I wanted to tell you. And I want to mention that, these folks here are the ones who actually do all of the heavy lifting when it comes to these kinds of experiments. In particular, I want to highlight Dr. Justin Lane, who former PhD student in the group, he's now a postdoc at Yale, really got us on the road to superconducting qubits. Dr. Heejin Byun, who is a postdoc at Sandia National Lab, really, when he was a PhD student, got this electron on helium work going. Lianji Zhang is actually now working here in Ural's nanofab. And he did a whole bunch of stuff on 2D electron systems that I didn't get to tell you about, but he gives he could tell you about that himself. But yeah, these are the folks that actually do this work. I'll also mention, here's a plug for the Superconducting Qubit Quantum Acoustics project. We have a postdoc opening, so if you know of anybody who's interested and thinks that kind of stuff is fun, just reach out to me. And finally, this wouldn't be possible without my collaborators at MSU, of course, the folks here at WashU that have been instrumental in a lot of our qubit work and other stuff, and the folks who support this work from the funding level. And with that, I'll take any questions that you have.
What is the term transmon somewhere? What was that?
Yeah, so transmon is it's old language. It's essentially that you're coupling the qubit to a transmission line resonator. It's just jargon. All we're doing is using the microwave. It's jargon. It's just an old name that people came up for this particular kind of qubit. Transmons are often referred, as transmons are in some sense distinct from, say, a Cooper pair box or a charge qubit that has very strong coupling to charge oscillations. The transmon energy levels are tuned in such a way that they're maximally insensitive to charge fluctuations. So that gives you some idea, but the word is just terrible naming.
You had a specific number for the electromobility on helium.
Yes.
So how, is it just time of flight measurement?
No, you can do just, so your AC coupling to the electron system, you can't make ohmic contact to it. So you're always measuring things capacitively. But so what you can do is you can model, actually the right way to think about this electron system is as a distributed 2D transmission line. And within the context of that, that transmission line has some loss. And then you can infer from fitting that your data to that transmission line model, you can extract a mobility.
In that case, wouldn't you need to know the density of the electron?
Yes, and so you have to independently know that, and you can infer that from, I didn't show this, but you can infer it from field effect transistor measurements. So if you have these 3 electrodes, you can essentially deplete various portions. I actually have a backup slide on this. Why don't I just go to that? Not that. There's a gap. This is not. Whoop, that's something else. Where this is the transport stuff. I hope I have a backup slide on this. Otherwise, we're just going to be electrons. Where are you? Here. So this is you can do transport data on the electron on helium system. So if you have these 3 electrodes, you can essentially have a source, a gate, and a drain. This has no surface acoustic waves. We're just doing AC transport. And so you can, this is the gate voltage. If the gate voltage is very low, essentially no electrons live here in the middle, and the electrons are only on either side, no current flows through the device from the source to the drain. But as you make this more and more positive, electrons enter into this region and current turns on. And essentially from the width of this turn on voltage, you can make an estimate of the electron density and geometry and capacitance.
Because if you have, usually you have a field effect transistor, the source is providing the electrons through a channel, right?
Yeah.
But you have a finite and you have helium.
Exactly. So this is a very, very weird field effect transistor because it works with fixed numbers of particles. So you can see like here, all the electrons are there. They're just on the left electrode or the right electrode. Then they get distributed across all the electrodes and current flows. But if you keep increasing the gate voltage, then all of the electrons land on that middle electrode and no current flows. So I'm just redistributing these particles around. There are no sources. There's a fixed number of particles there. Cool. And the capacitance lets you estimate, when you put the electrons down, you can see how much of a capacitance change you get. There's all kinds of, actually we have a paper on this. This paper has a whole lot of detail about how to estimate all these densities and things. This is not, we didn't come up with any of that. We just used it and wrote it down for people.
Question. That's very impressive. You get very high mobility.
Yeah.
So is that chimera by cyclotron mobility?
Yes. Oh, this is a great question. Yes. So people have done cyclotron resonance measurements on this system a long time ago. And I'm forgetting now the detail.
Mobility, because I heard a device people use
Yeah.
transistor device mobility very different from.
Yeah,
cyclotron.
you do find a high mobility in both cases. This is my recollection. We've not, but
It's very possible to see quantum Hall and fraction quantum Hall because that's a typical limit.
yeah, so here it's really not possible to see that physics because so fractional quantum Hall is certainly, you need a quantum degenerate system. You need a system where the electronic wave functions of individual electrons strongly overlap. We're at far too low a density. We're in the regime where we have essentially a classical electron system that can then crystallize, not a quantum. Ideally, one would start, there's this, and this is an outstanding effort in the field. We're not working on this, but if you start with the electron, the classical electron liquid, and you turn up the density, the system will crystallize into a Wigner solid. If you continue to crank up the density, at some point the electrons start to overlap with one another, and you will enter into a quantum degenerate fluid. So that's called quantum melting, and that would be the precursor to being able to see things like quantum Hall or fractional quantum Hall in this system. But the density here is far too low, and no one has been able to achieve quantum degeneracy or quantum melting in this system.
That's a maybe elementary question because I teach solid state physics. I'm sometimes confused about it. Like here, we typically see the materials, many body quantum mechanics,
Yeah.
or like more classical. Typically, we compare kinetic energy and
Yep.
potential energy.
Yep.
if we density is lower, typically kinetic energy is smaller.
Yeah.
And the potential energy is stronger.
Yeah.
And in those cases, typically we think it's a strong correlated case.
It is. So if you move
Just more quantum.
Yeah, yeah, Mark Dickman would love that you said this. So in fact, so this is, the transport behavior of this can't be fully understood in terms of classical Drude physics. You must take into account the fluctuations of, the quantum fluctuations of each electron in renormalizing the transport properties locally because of these highly correlated effects. The Coulomb interaction really does correlate this, and it is a quantum mechanical problem that you have to take into account. Mark actually figured out that theory a long time ago, and it matches well with magnetotransport data. But you're absolutely right. Other questions?
This is a dumb question. Can you apply enough voltage to suck the electrons down?
Yep.
Through the fluid?
Yep. You can, if you apply some, and they'll actually form bubbles
Yeah.
under the surface, and it'll form a little cavity, and the electron will sit in the center of that bubble. There's a whole subfield of people that, yeah, and so you can balance the buoyancy of that bubble with the downward force of the electric field, and you can get a mobile electron bubble system underneath. But the bubbles are big; they're like nanometer scale, with a single electron hiding out. And then there's a whole subset of folks who are working on multi-electron bubbles. You can make a bigger bubble where the entire interior surface of the bubble is covered with electrons. Those are very complicated experiments. We don't do any of that.
But very interesting also.
Yeah.
Is there any advantage of having a system where you, instead of electrons, you put, say, magnetic ions or
Oh, this is a
something?
great question. So people have tried this relatively recently. There's a group in Japan that tried to do this. I don't think they tried magnetic ions, but they tried trapping ions on the surface. And what they found is that, I think they didn't push, I don't know if they're still doing it, but what they found initially is that there's clustering problems. So the ions end up sticking together in kind of annoying ways and then sinking and forming these clusters that just, it turned out to be a bit of a mess, is my understanding. But I don't.
So why ions will behave differently than electrons?
I don't know. I'm no expert in ions. But in principle, I think this is a good idea. And people have, it's so good that I know that there is a particular experimental group that has tried it. And I don't know, I think they were trying to use laser ablation to create the ions. So maybe it's something specific to the technique that they were using that was making a particularly dirty kind of snowball kind of situation on the helium. But it's not a bad idea. It's just, the field is relatively small. There aren't that many groups that, it's kind of technically annoying. It can be technically annoying, but also fun when it works. Oh, is there a question in the chat? Or is this?
I think that's the old one, but.
Is it? I don't even see it. That's a single electron transistor. Other questions? Anybody in Zoom have a question? Are you all still there? It's always.
Yeah, there's 6 of them.
Yeah.
All right. Well, if not, let's thank Johannes again.